Hi everybody and welcome to my video on the Hubble constant. Today I want to focus on local measurements of the Hubble constant and explain to you how those lead to what we call the H0 tension. This is something that has come up only in recent years due to the high precision measurements that we are able to perform nowadays. When I was thinking of how I want to structure this discussion, I came up with a, in my opinion, very scientific approach, namely simply asking questions. This of course leads to more questions and not so much to answers, but we'll give it a go anyways. We'll start off with asking the question, what is the H0 tension? And for the ones that are a bit unsure what H0 actually is, or the ones that simply forgot, we'll recap and ask the question, what is the Hubble constant? The next question you might ask yourself, which is, how do we actually measure H0? This has a lot to do with measuring distances, and during that discussion, you'll hear the keyword standard candles. So the next question will be, what are standard candles? With this information, we are ready to understand how measurements of H0 were recently improved using supernovae. We will also ask the question, are there other kinds of methods that measure H0 besides using standard candles? Finally, we will ask the more critical questions, is the Hubble constant really constant? And are there ways to resolve the H0 tension? Okay, so what is the H0 tension? As I mentioned previously, the H0 tension is a very recent development, but it is considered a very serious issue. If we plot all recent measurements of H0 using various methods, we get this. In the upper region, we have results coming from the CMB, baryonic acoustic oscillations, Big Bang nucleosynthesis models, and galaxy surveys. The middle shows local measurements. SHOES uses supernovae mainly, CCHP uses red giants to estimate distances, MIRAS uses so-called Mira variable stars. Holy Cow is a collaboration that uses strong gravitational lenses to get H0. MCP uses megamasers, and SBF stands for surface brightness fluctuation. We can see that early measurements tend to lower numbers, late measurements to rather higher values. The issue here is when we compare them to each other. For example, SHOES and Planck stand in a 5.2 to 6.4 sigma tension to each other. In other words, there is a 1 in about 20 million chance that both measurements contain the truth within their error margins. This really shows how serious this issue is, and that's why we call it H0 tension. However, if we look at the entire history of measurements of H0, starting with 1929, H0 measurements seemed to converge to a single value, especially since the invention of CCD camera sensors in 1959. The Hubble constant is usually cited in units of kilometers per second per megaparsec, which is, coincidentally, almost the same as 1 inverse terayear. Theoretically, the Hubble constant is today's value of the Hubble parameter. It describes the expansion rate of the universe, which is time-dependent. To see that, let's shortly derive the Hubble parameter. Okay, so our first goal is to derive the Friedmann equation. This actually requires GR, but we can also derive it in Newtonian physics using some assumptions. First, we assume a homogeneous and isotropic universe which is expanding. We then can divide it into two regions, one inside the sphere and one outside. The sphere has a radius r, at which we place a test mass m. Because of the expansion, m is moving with the sphere at speed v, which is r dot. We can now write the Hamiltonian of this system, which is simply the kinetic energy plus the potential energy. The density inside the sphere we write as ρ. We can then introduce new coordinates for r and write it in terms of a co-moving distance. Here, a is time dependent, x on the other hand is not. We can replace the expression in the Hamiltonian and get half m a dot squared x squared minus 4 pi over 3 gm rho a squared x squared. Now we just have to divide by 2 over m a squared x squared and rearrange to get the Friedmann equation. A dot over a squared equals 8 pi g rho over 3 minus k c squared a squared, where k is minus 2e over mc squared x squared. In a flat universe, the last term is 0. The Friedmann equation is in units of 1 over time squared, so in a way we have an equation of motion for the entire universe. And remember, v equals r dot, which we can split into a magnitude and a direction. And if we insert the same change of coordinates, we get v equals a dot over a times r, which of course is simply Hubble's law. So, if we take the Friedmann equation today, we have a formula for the Hubble constant if we know the density distribution today. Now you know what the Hubble constant means theoretically, but let's go back in time about 100 years in order to answer the question from an astronomer's point of view. In 1919, this gentleman by the name of Vesto Melvin Slipher recorded the light spectrum of the Sun. And when he compared it to other spectra from other objects, which turned out to be other galaxies, he discovered something very peculiar. He saw that spectral lines from the Sun also appeared in spectra from galaxies. However, the lines seemed to be shifted. He eventually realized that this shift was due to the Doppler effect and used it to calculate velocities for each galaxy. And what he found puzzled him. He found that almost all galaxies were moving away from us. In 1929, it was Edwin Hubble who took Slipher's data and compared it to his own distance measurements. And this resulted in the probably most famous plot in cosmology, the Hubble diagram. What he concluded from this diagram was that the universe was expanding. By looking at his slope, I estimate he found a Hubble constant of about 500 kilometers per second per megaparsec. Now this already shows us how we measure the Hubble constant. On the basic level, we need two parts. The first is measuring the recession velocity, which we can get from measuring the redshift. The second part turns out to be a little more complicated. We have to measure distances to astronomical objects. There are several ways of estimating distances in astronomy, but interestingly, the basic principles can also be applied here on Earth. The first method is probably the most simple. It's called the parallax method. If you have 2 points of observation and you know the separation between them, you can build a triangle. And if you know your trigonometry well enough, you can work out the distance to that object without ever going there. On sea at night, ship captains have another way of telling distance. They look out for lighthouses. They know that lighthouses are extremely luminous, and as long as they appear dim, they know that they are still far from shore. Light gets dimmer with distance. This is something that we know intuitively, but it was actually Newton who realized that objects get half as bright with 4 times the distance. We call this relationship the inverse square law. But how do ship captains measure distances when the weather conditions are bad or when it is foggy? Then they use foghorns. They use sound waves, something that reminds me a little bit of how we measure H0 using BAOs. The last method I can think of only works in a particular situation. Have you ever stood on a cliff, couldn't see the bottom and still wondered how far it is to the ground? In some cases, you can use an easy trick to estimate the distance. Let a rock fall down and listen for its impact while counting the number of seconds. The distance to the ground in meters is then simply 5 times the number of seconds squared. Measuring distances in space is not much different from these methods here. Most commonly, astronomers actually look for lighthouses in space. Of course, they don't call them lighthouses, they call them standard candles. Standard candles are objects of known brightness. Those are interesting because, as I mentioned, when we know how bright things are, we can calculate the distance quite easily. So standard candles are an integral part of measuring the Hubble constant based on brightness. And one of the two most commonly known standard candles are Cepheids. Most stars are constant in their luminosity, up to a few percent. Like the Sun, they have a steady outflow of energy from their interiors. However, some stars are seen to vary in brightness, and for this reason they are called variable stars. Cepheids are a particular category of variable stars. They expand and contract periodically, therefore changing their brightness and color because they reached an unstable stage late in their lives. One of the better known Cepheids is Polaris, the North Star. Cepheids have been known for a long time. However, it was Henrietta Leavitt in 1908 who made a remarkable discovery while she worked as an assistant in Harvard. She plotted the periods of Cepheids against their brightness and found them to be linear in log space. This means, in order to measure distances to Cepheids, the only thing you need is a telescope and a clock. The next standard candle I want to talk about are supernovae type 1a. You probably all know what supernovae are, powerful explosions of stars, but some of you might not know what type 1a's are. Only a specific configuration of binary stars will explode in a type 1a supernova. Thus they are quite rare. The general rule says you have one type 1a supernova per galaxy every 100 years. Of course, if you look at enough galaxies, you should be able to find one every few weeks or so. The binary system that leads to a type 1a supernova first needs one of its stars to become a white dwarf. The mass limit of a white dwarf we all know from Chandrasekhar. It's 1.44 solar masses. After that, the electron degenerate pressure is not enough to stop its complete collapse. And eventually, the second star will become a red giant. So it will expand, and it will expand so far until the white dwarf can siphon off the gas from the red giant. When the white dwarf reaches 1.44 solar masses, it goes supernova, and that's why supernovae type 1a are standard candles, because they always explode at the same mass limit. Usually, those standard candles are used in conjunction with each other. One method measuring closer distances usually provides calibration for the next one, and so on. This is why we call it the cosmic distance ladder. Okay, so with what we have learned so far, we have a much better understanding of what research groups do when they actually attempt to measure the Hubble constant. One of the leading groups in that field is led by Adam Rees, who was joint winner of the Nobel Prize in 2011 with Brian Schmidt and Saul Perlmutter. In 2016, he published a paper in which he presented a revised measurement of the Hubble constant. In it, he describes that by increasing the number of Cepheids and supernovae alone, and better distance calibration to the Large Magellanic Cloud, he achieves a 2.4% determination of the Hubble constant. Often, this gets picked up by the media and grossly embellished, which leads to headlines like "Mystery of the Universe's expansion rate widens with the new Hubble data." In the latest publication, Adam Rees's collaboration reports on an already 1.8% determination of the Hubble constant. So the 1% level isn't far off. Now you might ask yourself, are there other methods or better methods to measure the Hubble constant in the local universe besides using standard candles? And the answer is yes. In the middle of Messier 106, for example, we have what is called a mega-maser quasar, which is probably the most astrophysical name I have ever heard. So what is a maser? If you think of laser, you're almost right. Laser is an acronym and means light amplification by stimulated emission of radiation. Maser is also an acronym and stands for microwave amplification by stimulated emission of radiation. So by the name alone, we can tell that it must be a very bright microwave source. The amplification happens when we have atoms in an excited state. As soon as a photon comes by, it can trigger a transition to the ground state, which causes another photon to be emitted at the same frequency as the first photon. If this happens often enough, we have sort of a runaway effect, which we then call maser. The cool thing about masers is that we can measure their phase-space positions with incredible precision due to their brightness. This is such an example. You can see a maser gas cloud moving around a central black hole in a tilted disk. We have one cloud moving towards us, another cloud moving away from us, and a third moving sideways to us. This happens at almost Keplerian velocities. And how we can derive distances from masers, we will see now. Okay, so the distance to a maser can be calculated geometrically. To see that, let's make a drawing of such a system. We have an orbit around a black hole at some distance. On that orbit, we have two blobs of gas with masses m2 and m1. m1 is at a distance r1, which we cannot measure, but we know the angle theta. m2 is at a radius r2, has an inward acceleration a, and moves with a velocity phi dot. The black hole has a mass of just m. The observer at the other end can measure the velocity 1, theta, a, and phi dot. And of course we want to know the distance d. Let's work out blob 1. We can measure theta and this gives us r1. r1 is just theta times d. Furthermore, we can balance centrifugal forces against gravity, so we know that m1 times v1 squared over r1 equals gm m1 over r1 squared. This can be rewritten as m equals theta d v1 over g. For blob 2, we can write the equation for the acceleration. A equals v2 squared over r, which gives us the radius r2 as r2 equals v2 squared over a. And similarly, we can write again gm m2 over r2 squared equals m2 times v2 squared over r2, which gives us another expression for r2, which is gm over v2 squared. We now have two expressions for r2 which can be equated. A equals v2 to the 4 over gm. We cannot measure v2 directly, but it can be expressed as phi dot times d. This then gives us the mass as phi dot times d to the 4 over g times a. This brings us to the final step, where we can equate equations from blob 1 and 2 for the black hole mass. So theta times d times v1 squared over g equals phi dot times d to the 4 over g times a. And rearranging gives us finally the distance. D is the cube root of theta times v1 squared times a over phi dot to the 4. Another method, which I am using in my own research quite often, is completely independent of the cosmic distance ladder and can measure the Hubble constant with strong gravitational lenses. Hereby, time delays from lens quasars are measured. In the multiply imaged quasar, a change in brightness can be detected at different times in different images. This time delay, the difference between arrival times in one image to another, can be translated into a physical distance, which is proportional to the inverse of the Hubble constant times the speed of light. A major collaboration which works with these gravitational lens systems calls itself Holy Cow. They have currently published their 14th paper on that subject, so if you're interested in knowing more, there is definitely enough reading material around. The second to last question that we ask today is the Hubble constant really constant? This is very speculative, and we will not be able to answer this question today, but we can still discuss it. The Holy Cow collaboration's latest paper presents measurements of H0 from 3 different lenses and suggests that it might not be constant after all. They find that at different locations in space, at different times and different angles, the Hubble constant takes different values for each system. The interesting part is that the closest system seems to have the highest value of H0, whereas the furthest has the lowest value. The values they got came from a blind study, meaning that they didn't look at the results until the very end, and good scientists would publish that result no matter what it is. What they got were values that were completely different from previous measurements, with the highest value being 82.7 kilometers per second per megaparsec and the lowest at 70.1. These results seem similar to my own experience. An analysis of a single lens tends to result in various values of H0, with errors not rarely being above 10%. The final question of today is, how can we resolve the H0 tension? When one method to measure H0 gives us a value of 74 kilometers per second per megaparsec, and another method gives us 67, which is a difference of about 9%, and both are certain up to less than 2%, then somebody has to be wrong. The easiest explanation, which is at the same time the most boring one, is that somebody is affected by unknown systematics. However, these results might be hinting that the universe's expansion rate isn't constant after all. It is also possible that some regions of the universe might be expanding at different rates than others. This is a weird thought, but there's nothing in cosmology we know that excludes this possibility. What definitely will be interesting in the next few years are results from LIGO. By looking at gravitational wave signals of colliding neutron stars, which are called standard sirens, we can obtain another measurement of H0, which might be able to shed some light on this whole situation. Thank you all for watching. I hope I gave you some ideas to think about, and if you have any questions that you want to ask me, you know how to contact me. Stay safe. Goodbye.